We'll give a couple minutes for stragglers to show up. Got to cycle in with no rain. That's always a bonus. We had some lag last time between Maricela, the teaching assistant, and me with the questions from the chat. So we've gone to a Slack group. Hopefully that should make that communication come a little bit faster. Anyway, we'll see how that goes and if it helps. Okay, let's make a start. I'm going to take one step back today. There's been enough questions about assignment 1, question 1, that I guess I want to go through the setup of that. I had assumed that everyone would know how to start that question from their previous backgrounds. But like I said, I've had a few questions. I'd like to make sure everyone at least knows how to proceed with that question. Now, of course, this is a little bit of a fine line. I want to make sure that everyone can at least engage with the material. But I know there's a lot of students out there for whom this is still fresh in their minds, the background material. And so I want to spend some time on it, but not too much. Anyway, we'll see if I can hit that balance. I will try and present things in a slightly different way than you had seen them before, following up on how I started in the first lecture. So at least hopefully that will make things interesting for people, even if they know what they're doing. Okay, so let's look at our boundary value problem, this first one that we're looking at. We had an unknown u of x, and we're trying to solve it so that it satisfies this differential equation with given data f and boundary conditions. And remember, I wrote this whole problem as symbolically L for linear times u is f. And when I write this L, right, this includes the differential equation and the boundary conditions. So dE for differential equations, and BC's, that's boundary conditions. And if I write it like this, then, and I say it's linear, then this, in your imagination, I have a powerful imagination, I don't know about you guys, you can imagine that it looks like a linear algebra problem, right? Which should be old news. So that's a matrix A times a vector U is a vector F. And there is this nice way of solving that problem when the matrix A is symmetric and there is a basis of orthogonal eigenvectors. And we went over that in the first lecture. And we showed that this L is symmetric in an inner product. So it has orthogonal eigenfunctions, and we can do the solution in the same way. Now, one of the things that confused some students in the first assignment is what exactly are we looking for when we set up the eigenanalysis? And so maybe I should have added a description. We're looking for eigenfunctions phi of x and eigenvalues, lambda, so that L times phi is lambda times phi, and phi is not the zero function. So remember, L includes the boundary conditions, right? So we're looking for something that satisfies phi double prime is lambda phi, and phi at 0 is 0, phi at 1 is 0. Now, if you look at this, right, one of the things that you can see right away is phi identically 0 does solve that for any lambda, right? So you're looking for special values of lambda, basically where L is not invertible, so that you can have some non-zero solutions. That's exactly the game that you play finding eigenvectors and eigenvalues. You're looking for where the determinant of the matrix minus lambda times the identity is 0. That's when the matrix is not invertible, right? And it's the same kind of game here. Well, now there's some cases, right? I could look at lambda equals 0, right? Then phi double prime would be 0. That would mean that phi would have to be a plus b times x. That's the general solution, right? Two arbitrary constants. But if I put that into the boundary conditions, then a has to be 0 from the first one, and b has to be 0 from the second one. So I have phi identically equals 0. That just tells you that lambda equals 0 is not an eigenvalue. What about lambda positive? And a nice way to remember in this example, and it makes the algebra nice, is if I say lambda is mu squared with mu some number, then I know that lambda is going to be positive. So then I've got phi double prime minus mu squared phi is 0. This is a second order differential equation with constant coefficients. And so there's this recipe, which you would have had in Math 215 or whatever equivalent course you took as a basic ODE course. This is the sort of material I'm assuming that you know and remember. And some students have indicated that it was a while back. I think you've got to go back and look at that material, but I'm going to help you out this one time. The recipe says you look for solutions of the form e to the r x. And if you plug that in there, you get r squared minus mu squared is 0. It's a quadratic equation. Of course, there's two roots. Here, these roots are easy to find. They're plus or minus mu. And that tells you that the general solution of this thing that we wrote down, which is the eigenvalue problem, is phi is some constant e to the mu x plus some other constant e to the minus mu x. And in the notes to the first assignment, it said that if you can use hyperbolic trig functions, it will make some of the algebra easier. Well, this is certainly the case here. I can write equivalently. I can write it as a linear combination of hyperbolic sine and cosine functions. So this is a hyperbolic sine mu x. Oh, maybe I should use different letters. D hyperbolic cosine mu x, where these guys, as the definition of hyperbolic sine, it's e to the x plus, minus e to the minus x over 2. And hyperbolic cosine is e to the x plus e to the minus x over 2. Okay, and So really using hyperbolic cosines is just sort of a change of basis of one form to another, right? You can get C and D from A and B with just linear algebra, and it's invertible. So this is just a different way to change it. And the nice thing is, of course, hyperbolic sine of 0 is 0. So that's going to make applying the boundary conditions easier. Hyperbolic cosine of 0 is 1. And if you look at their derivatives, it switches. Right, so this is a useful combination. So if this is the form of my solution, then to satisfy the first boundary condition, I have to have D equals 0, right? And then to satisfy the second boundary condition, I have to have C times hyperbolic sine of mu is 0. And the graph of hyperbolic sine looks like this. So it's not 0. So that means I have to have C and D both 0 to satisfy the boundary conditions. Lambda bigger than 0 is not no eigenvalues here. Right? This is what you do for completeness. If you've done this problem before, then you know that there's only negative eigenvalues and you're going to get the sine series. But if you had seen this for the first time, which you would have maybe a few years ago, this is the game that you would play. Okay, so now let's look for negative eigenvalues. So again, it's convenient in this case to say it's going to be minus mu squared. Right, so I'm going to have phi double prime is minus mu squared phi. That's phi double prime plus mu squared phi is 0. Now I'm going to do the same e to the rx solutions, and I'm going to get r squared plus mu squared is 0. These are complex roots, which will always come in a complex conjugate pair. And so that tells me I have solutions A sine mu x plus B cosine mu x. Right, and if R is any other complex conjugate pair, then you can look back through your Math 215 notes to figure out what the general solution is, and that's what you need to do for assignment 1, question number 1. Okay, so now if I'm going to apply the boundary conditions, that means this term can't show up. And then if I apply the next boundary condition, that tells me that A has to be 0, so not an eigenvalue. Unless sine of mu is 0. And that's what tells me that mu has to be n times pi. Remember, the eigenvalue then was minus mu squared. That's minus n squared pi squared. And the corresponding eigenfunction is sine n pi x. Okay, and then now we know theoretically that these functions satisfy an orthogonality relationship. But the first time you saw that, you did it explicitly, did the integrals of sine n pi x times sine m pi x, where n was not equal to m, and you showed that that was 0. And when you get to that part of question number 1, where you think that you're going to have to do some work with the weighted inner product, if you've done things right, you will see that that part is actually really easy. Things fall out in a nice way. Again, this is something where I'm trying to hit the fine line between helping people get started and not boring people that are already on this page. Hopefully I've hit the right note. Maybe I'll stop here and ask if there's any quick questions on this presentation. Okay, no questions seem to be coming in. Let's go on with the material of the day. So this is the week where we derive some of the equations that we're going to look at. So last time we had the stretched spring linearized and scaled, leading to the simple boundary value problem that I wrote up today. And if you look in the same notes that were presented or posted for last lecture, you can see how you can continue that derivation to a time-dependent problem and get the wave equation, which we will consider later on in the course. But if we're going to have our first PDE, which is going to involve time and space derivatives, there's an easier equation to start with than the wave equation. It's the heat equation. Okay, it only has one time derivative, and it has a bunch of features which make it, let's say, a less delicate problem to look at. So I'm going to derive the heat equation today. And it'll be the mathematical aspects of the heat equation will be the topic for next week and possibly the week after that. So I'm going to derive it from thermal conduction in a thin rod. And there's posted notes. I'm going to add some volumetric heating to it, so that I'm going to get a forced heat equation. So that'll be what I'm going to do is going to have an F in it that wasn't there before. Okay, so what's my setup? I'm going to have the thin rod. There we go. It's going to go from x equals 0 to x equals L. And of course, you know from last lecture that at some point we're going to scale x so that there's a scaled dimensionless x that goes from 0 to 1, which gets multiplied by L to get back to the scaled variable. So here's my thin metal rod. And I'm going to look at the temperature in a cross section at a given point x. And I'm going to say, and this is something we're going to follow up on when we get to heat equation in higher dimensions. We'll look at the radial aspect of the temperature. But for now, I'm just going to say it's okay to take this as approximately constant. On this cross section. So it's going to vary in x, but it's not going to vary in the cross section y and z coordinate. So I'm going to have a temperature U, right? It's going to be a capital U because I'm going to end up with a little u that's going to be a scaled version of this. It'll depend on x and t. Okay. So I'm going to say the temperature is held constant at the ends. So I can look at U at x equals 0 for all time. Now in the notes, there is, it adds a a non-zero temperature, but we know how to handle that. So let's say it's I'm just going to hold it at a temperature that I'll actually call 0. So whatever the temperature was, I'm measuring it against this ambient temperature. So use already, I've messed with it a little bit. It's a difference to ambient. And if I look at the temperature at the other end for all time, it's also going to be 0, just to simplify things. So I'm going to have volumetric heating. Right? So this could be coming from an external source. I always say it's your sibling with a blowtorch on the rod, okay? And the sibling is awake, right? So that it's moving the blowtorch around. So the volumetric heating that's coming in is going to be a given. This is going to be given data. In other problems, it actually could depend on you as well, if you have like a Newton law of cooling term at the boundary of the rod, but we're going to assume now that it's just given. Okay, so just like last time, so I'm going to foreshadow the result. Okay, so after scaling x and t and u, we will get a dimensionless problem. We're going to have u, well, t is going to get scaled to tau, that's scaled to time. The time scaling is interesting, actually. I'm going to have u, y, the second derivative. This is du d tau. And this is d2u dy squared. So it's actually a PDE, right? I got derivatives in more than one variable, right? So we've got a PDE. Week 2, we didn't have to go past week 2 to actually get a partial differential equation. There's going to be a scaled term here for the external heating, and I hope it's clear. I've got big U's for the dimensional variables and little lowercase letters for the scaled variables with. Okay, and okay, no surprise. I can tell you already that x will be L times the dimensionless variable. Oh, look at that rainbow pen. Oh, I like that. Okay, so that's what's going to happen. Let's get to work. We're going to have 2 steps just like we had before. There's some mathematical modeling. That's where we have to put some physical mechanisms into mathematical equations. And then we'll do scaling, non-dimensionalization. The problem that we're going to have is already linear, so I don't have to linearize it. I don't have to have the epsilon thing going on like we did last time. So we're trading difficulties. Now we have a time-dependent problem, which is new, but it's already linear, so at least we don't have to worry about that part. Okay, so there's 2 experimental observations that go into the modeling. And remember that this is the game which you may be playing later on in your career, which is you want to optimize some process. And you can do some experimental work, but you don't want to do it all experimentally. if you think back to the old days of aeronautics, well, even in the old days they did this, right? You know, you would have a new design for an aircraft, and you'd build a model, and you'd put it in a wind tunnel, and you'd see what would happen, right? Well, wind tunnels are really expensive. I mean, they're expensive to build. They're expensive to run, and it's time consuming, right? And so now it's not like people don't do experiments on wind flow over airfoils, but aircraft are designed mostly computationally, right? So you want to have as few experiments as you can to understand the phenomenon, to model, and then use your pencil and paper and computer to do some of the work. And so that's what we're doing. I'm talking about experiments, but these are experiments that are, let's say, relatively easy to do and get accurate results from, which then you're going to combine and describe more general phenomena. Okay, so here's the first one. I'm going to have a material. This is the metal in the rod. It's just going to be a lump, though. It's not going to be the rod. I'll have a sample with mass. Oh, my writing sort of got a little wrong there. So I got a material sample, mass M. It's initially at temperature some initial temperature, heat, some amount heat, Q. Well, so this mass, this is in kilograms. Q, this is in joules, is added. And you see how much the temperature is increased. And temperature increases to a higher temperature. It is found, if you do these experiments, that the temperature change is approximately proportional to the amount of heat you add divided by the amount of mass that you have. If you've got more mass, you have to add more heat to raise it up the same amount. And if you add more heat, you can heat it up more. So let's express this with a constant C. Q divided by M is C times U1 minus U0. Okay, and for solids, this constant C does not depend on M. And it also does not depend strongly on the initial temperature in a range. Here's where the linearization is happening, right? If you look at a long range of temperatures, well, then of course we could have phase changes where all kinds of different things happen thermodynamically. So we're definitely not melting the material, right? But we're talking about small temperature changes have this linear response. Okay, and so let's make sure we've got the units right. This has units, joule per kilogram degree Celsius. And there's an interesting thing in the notes. This C for solids is basically just a number. If you're talking about gases, there's quite different behavior depending on whether you're talking about raising the temperature at constant pressure or at constant volume. So there's There's different things there. For solids, there is a difference between those two things, but it's not that big. So in words, the C is the energy that you need to heat 1 kilogram of the substance up by 1 degree, right? Okay, so let's let rho be the density. This is the mass density. And that's kilograms per cubic meter. Again, this density can vary with temperature. That would introduce some nonlinearity in the problem that we're talking about, but let's assume that it's roughly constant with temperature. So if I look at C times rho, okay, and let's look at the units of this. This is, units are joules per cubic meter degree C. This is known as the volumetric heat capacity of the material. And it's the energy required to heat 1 cubic meter of the material by 1 degree Celsius. Okay, volumetric heat capacity. There's one experiment and some units to go with it. Let's look at the other experiment. This is about heat flux. I'm going to have a piece of the material with a constant cross section. And I'm going to maintain a temperature at the two ends that's different. And I'm going to look at its length. I'm going to look at its constant cross-sectional area A. And I'm going to measure the heat flow through the substance. So I'm going to have F is going to be the heat flow through the material. It's going to be at steady state. So at steady state, the heat flow has to be uniform through the length of this thing. And the experiment shows that the amount of heat flow is proportional to the temperature difference and proportional to the cross-sectional area. Okay, I got a message from Slack, but it's from Slackbot. Okay, so not a student question. Okay.
Almost as bad as Team Snapchat.
Okay, oh, where was I? Okay, so the experiment shows that this heat flux is linearly proportional to the temperature difference. So if you double the temperature difference, you get double the heat flux. It's linearly proportional to the cross-sectional area. If you double the cross-sectional area, you get double the heat flux. Oh, there is a question coming through on Slack. What does steady state mean in this context physically? It means you've held both ends of this rod at this temperature for long enough that there's no time dependence in the heat flux that you measure. Does that make it clear?
Yes, thank you.
Okay, good. So the other thing is that it's inversely proportional to the length L. If you double the length L, then the heat flux that goes through here is half as much as it was before. And if you put all of those things together, well, there's a constant of proportionality. So here's this material constant. Okay. And it's proportional to the cross-sectional area. It's proportional to the temperature difference, and it's inversely proportional to the length. Where this K, this is independent of L and A, and it has units, joules per second per meter degrees Celsius. So I can also simplify this a little bit. I can think of the heat flux per unit area. So that's F divided by A. J is something that's often used for a flux in this way, flux per unit area. So I can look at that. And I can also take the limit as L goes to 0. And I can get J is minus, because this is left minus right divided by the distance between them. So I'm going to get a derivative, but I'm going to get a minus of the derivative. This is going to be minus K times du dx. Okay, so I've got a heat flux depending on temperature differences. I've got how that heat flux changes the temperature of a substance. So now let's do the modeling part. So now I'm going to go back to my thin rod. And here I go. I'm going from 0 to L in X. And I'm going to look, as usual, at a little piece of the rod between these two places. But I've also got time. So I'm also going to consider it between two times that are close together, because I got to get space and time derivatives out of this thing. Okay, so let's look at time 0. So we're just going to look here at this little piece of the rod at this one time. And I can look at the heat flow into the this little piece at the left. So I know that the heat, this is the heat flux per unit area. I know that that's equal to minus K times du dx at x0. And if I want the total amount of heat coming in, then I have to multiply that by the area. So let me put that in. And if I'm looking at the heat flow into the piece at the right, well, it's exactly the same kind of thing, except it is got a sign change, because the heat flow is, this is the heat flow from left to right that's coming in. But if I'm on the right-hand side, I want the heat flowing in has got to have the opposite sign. So this is K times A du dx at x1. So now I'm going to think about how much heat is happening in this little piece. Well, it's going to be J0A, oh, I better put this, minus J1A. But then I also have to add the volumetric heating. That's the F at X. And just like last time, I don't have to worry about, I'm not taking derivatives of this term, so I don't have to worry about the X that I put in here. This X is anywhere in the interval, and when I take the limit, it just limits to the value at a single point, the left or right limit, whichever one you take. Well, that's the volumetric heating, right? So what's the total amount of heating? Well, it's got to be the volume of the piece, which is x1 minus x0 times the cross-sectional area. That whole thing here, that's the volume. So if you want the total amount of heat, it's the volume times the volumetric heating. Okay, so this is going to be, if I combine those things, I'm going to have a K times A times du dx at x1 minus du dx at x0 plus x1 minus x0 times A times F. Okay. Well, now I'm going to assume this heating term. This has units of watts, joules per second, right? I'm assuming that this heating is happening uniformly in the interval T0 to T1. So if you've got some heat coming into a little piece of material, it's going to heat up, but we know how much this material heats up with applied heat. Okay, so here is the amount of heat that's coming in. This is the rate. So if I'm talking about how much it heats up in that time interval, I have to multiply by the time that I've got that rate.
Brian?
There's a question from the audience. We're assuming no heat is dissipating to the surroundings. yes and no. I'm assuming that whatever is happening externally is captured by this F. So again, yeah, these are capital U's. Maybe that's not clear. Capital U's. If we had a heat dissipation that depended on U, then this F would also depend on U. But I'm not thinking of it that way. You can think of it that I'm thinking of this as you have to have two ideas in your head, right? There is, here's maybe the way to think about it, right? That you have, it's insulated on the edge of the cross section, but there is a heating wire in there that's applying some heat along the length. Okay, and that's what this F is. There you go. There's a physical picture you can have in your head. Okay, so now let's add up how much heat is coming in. Well, this is the amount of heat that is coming into that little piece of the rod per unit time. So the total amount of heat I have to multiply by the time that's active. So that's all of this. Okay, I don't want to write that all out again. Okay, let's find the rainbow. Where's the rainbow? There it is. So I'm going to take all of this and put it into here. And so this is now just a amount of heat entering the piece of the rod. Right? And that has got to increase the temperature of the piece. And well, I've got to take the volume of the piece. I've got the volume of the piece again. Times the volumetric heat capacity, that's the C times rho. And it'll heat it up by an amount U at T1 minus U at T0. And again, you notice that I haven't put an X here. These are the average temperatures in the piece. And there's no derivatives in X that are going to happen to these. So it doesn't matter where you evaluate those. Think of them as the averages. Just like over here, you can think of that as an average of F over the piece and over the time. Okay, so now I'm going to divide this thing by x1 minus x0 and t1 minus t0. And what am I going to get? I'm going to get the average temperature on the, this is the average in X. I'm going to get K divided by C rho. And if you want to be really careful about this, is these are the averages in time. And then I'm going to have the average. This is going to be an average in X and time. over the small piece over the small time of x and t. Well, okay. And then, of course, once you see this, we've gone down this path before. You know that I'm going to take the limit. T1 goes to T0, x1 goes to x0. The average things get averaged over smaller and smaller intervals and collapse to a single value. And the differences here turn into derivatives. So I'm going to have du dt over here. I'm going to have a k over c rho d2u dx squared. I'm taking the derivative of a derivative, so I'll get the second derivative. And I'll get 1 over c rho times f of x and t. Okay, this thing here, this thing is the only coefficients that's left in the differential equation part of things. This thing is called the thermal diffusivity. And remember, we're going to try and keep track of units to help us identify when things have gone wrong in our derivation. And if you check, the units of K are meters squared per second. That's a typical unit for diffusivity. Okay. So we've got this, and it's linear, right? So we don't have to do the work we did last time to linearize and look for small deviation solutions. Now, to be fair, right, there's already some linearization in here. I already said, oh, I'm assuming some of these coefficients don't depend on U strongly, on temperature. And of course they do depend a little bit. So there's the linearization though was front loaded with the behavior of the coefficients. But again, this is not going to describe the temperature in the rod if you heat it past melting temperature of the material, obviously, right? So this is this has some limited applicability with some temperature range, which you'd have to think about if you were looking at some kind of extreme case. Now we've got the next part is the scaling and non-dimensionalization. We didn't have a break last time because I could tell that it was going to be hard to finish the material in a timely manner. But this time I think we're on track. And I have a poll for us to have as a break. I'll have a sip of tea and you can do a poll. The poll is about how familiar are you with the variation of parameters techniques in ODEs? So have a look at that and tell me what you think.
In the meantime, is it possible to scroll up a little bit? I think I just missed a line in the notes.
Of course. Oh, sorry, I can scroll up on that screen as much as I want and it won't help. How about tell me when?
More? A bit more? Bit more? Bit more?
Oh, you
Okay,
want the rainbow. Okay, yeah. How about that?
Yes, thank Oh wait, could you scroll down a bit now?
Of course.
I want to make sure I got everything. Okay, I see. Oh wait, thank you.
Okay, so oh, I amused myself putting this poll together, as you could tell. Yeah, it's my close friend, but when I was an undergraduate, it wasn't. This is actually a technique that is going to come up as we solve the heat equation, various forms of data in the heat equation. And hopefully I will make it your close friend at the end of next week. We'll see. At least that's my hope. Okay. So here's where we're started, and now we're going to do the scaling. So far I've got oh, I like that red, but yeah, maybe it's too much. Okay, this one is not so important. Of course, you already know, right, that I'm going to scale x, right? So I'm going to have x is L times y, and this will be my dimensionless spatial variable. Y will go from 0 to 1. Scaling is useful for a number of reasons. One of them is when you're looking at coefficients of different terms in a model, you can then really tell which ones are significant, which ones are big, and which ones are small. Because in units, you can't really. The example I gave last time is if you measure something in meters or in millimeters, then the number could look big or small. You can't tell. The other reason, and you know, I'm interested in the sort of computational implementation of these models. You end up with better scaled numerical problems with fewer rounding error issues if you compute the scaled problem as opposed to the raw problem. Okay, well, so that one's easy. So now if I look at d2u dx squared, and I want to turn it into d2u dy squared, then x is just L times y, so you're going to get this. This is the simplest form of the chain rule with just a linear multiplicative change of variables. So now I've got du dt is k over L squared d2u dy squared plus 1 over c rho f of x t. What about the time scale? Right. So I had tau was my dimensionless variable, right, for time. That was the foreshadowing. So I'm going to have t times tau. And what should t be? Okay, and I think no, this is little k. Sorry, there's a question about I went from big K to little k. That's got the C rho in it already. So I'm talking about the thermal diffusivity, not the big K is thermal conductivity, I believe is the name.
Thank you.
Okay, so I want to do that. Well, okay, if I do that, then du dt becomes 1 over big T times d u d tau. Okay, and this is where you look and you go, I really should take T. If I want to really have this all in terms of dimensionless units, I'm going to take my time constant to be L squared divided by the thermal diffusivity. And we can check the units are seconds, right? So this is really a time, right? And then if I do that, I get du d tau, that's scale time, is, well, I've canceled that term out. This is just d2 u d y squared. And then I'm going to get plus L squared over K C rho times F. Okay, it's I've got a coordinate y, right, which is not x, so it's L times y. And then to get to t, I'm going to have L squared over K times tau. Okay, and this whole thing, I don't actually care about all that much. I'm just going to call it f of y and tau. Right? So now I've got du d tau is d2u dy squared plus f of y and tau. This is the form foreshadowed in ancient texts held by the prophets. No, foreshadowed at the beginning of the lecture. So I said I was going to non-dimensionalize the problem. Does anyone see something that still has a dimension in it? Yeah. This is still capital U. Okay, I tried to fool you so that I could ask this question and not telegraph it, right? U still has a scale. One of the interesting things about linear equations is when you look at the size of the variable itself, well, it's linear, right? Which means that if you scale the right-hand side, you just scale the variable, right? It's sort of dimensionless somehow in a way automatically. So there's no specific scale for U in this linear problem. You can use any scale you want, which is a little bit unsatisfying, maybe, but that's what happens with linear equations. Something that sort of I wondered about for a while. Okay, so let's talk about it. I'm going to say I have scaled it, so I'm going to have a little u with whatever scale is appropriate. One of the things you could do is to say, well, f has a certain size, and I can use that size to scale f so that it has size 1. And then that naturally will scale U to have also size 1. So you can look at that. Let's go on and talk about the problem that we can look at now, right? So let's look at the heat equation. Now we can look at the scaled heat equation in a bounded domain. So here's a nice thing to do when you're doing PDEs is draw a picture. Right? So I could write this all out algebraically, right? But I want to say I've got boundaries at 0 and 1. I've been giving temperature data, right? So that's a particular type of data you could give for this problem. That would be boundary data. Well, let's put the most general thing we could put. I've got U as a function of X and T. So here at 1, I could give some boundary data that varied in time. Right, I can do that. I can also give boundary data over here. Well, I've got the differential equation I can put in here, right, in this picture. Oh, plus F, right? And of course, it's a time-dependent problem, which means you have to give initial conditions. This equation is describing how the temperature changes in time, but you have to know what the temperature was at the beginning, right? So you also need initial conditions. So I have to tell you that U at all values of X at time 0, that also has to be given. And sometimes I call it U0, but now I've already used that. So now I have to think of something else to call it. I'll call it, what will I call it? V of X. So now I'm going to look at this problem and go, there are 4 types of data. Right? Or 3, depending on how you like to count, right? There's the U0 and U1. Those are the boundary data. You could lump those together into just one type of data, or say that it's different at the 2 ends. There's the V of X, that's the initial data. And then there's the F of X and T, that's the forcing. Right? That's the heat, that's your sibling with the blowtorch, right? That's the external heating. So I can say the theory says, well, that this problem here, the problem has a unique solution. And it's well posed to all types of data. Remember what well posed means, right? It meant that if you change the data by a little bit, you only change the solution by a little bit. And you don't want to be in the business of trying to get a handle on ill-posed problems because they don't really make sense. If you can change the data by an arbitrarily small amount and affect the solution by an arbitrarily large amount, then the solution doesn't make much sense. As the final thing to say, I'll remind you that we can solve these problems separately. Due to linearity. Right? I can have a solution U1 that solves the problem with U0 of t, but U1 of t identically 0, V of x identically 0, and F identically 0. So that's just one of these 4 things and the other 3 0. I can solve another one with the right boundary conditions, but all the other conditions identically 0. I can solve the initial conditions, but everything else 0. And I can have 0 initial conditions and 0 boundary conditions and only have the data. And then the solution to the original problem is just the sum of all of those guys. Okay, and this is what we're going to look at in the coming weeks, and there'll be different terms, different techniques to apply to different things. Oh, there's a question that came in. Well posed is an equivalent term to well conditioned. Well conditioned is a term that's used for finite dimensional systems. So a well-conditioned linear system is one where changes in the right-hand side don't lead to large changes in the left-hand side. So when you're solving A times U equals F, you can change F a little bit, but you don't change U by very much, right? But there's a finite number, right? If the matrix is invertible, that number could be big, but it's still like the way you can increase the changes in the right-hand side is still some bounded number. It's just big. So it's a little bit arbitrary how big something has to be to change it from well-conditioned to ill-conditioned. Whereas in this infinite dimensional setting, ill-posed is stronger than that. You can have, arbitrarily small things make arbitrarily big changes. So that's what can happen in the infinite dimensional case. It makes it a clearer thing. There's no arbitrary sort of boundary between well-conditioned and ill-conditioned in the linear algebra case. In this partial differential equation case, it's like okay, yeah, there's no arbitrary threshold. You can certainly talk about things that are sensitive, right? And then there's an arbitrary amount. How sensitive do you have to be sensitive to some types of data? Anyway, to go back to this division here, what are the sort of techniques that we have, right? We've got some series techniques. we'll be able to use the same eigen sine series, eigen analysis for space. We can use that here. And we'll also have some other techniques that are going to come up. Green's functions, in this bounded case, we won't get too much of, but we'll be able to talk about them in sort of general terms.
Can I still use them?
Of course.
Wonderful.
You asked that before, but my answer won't change. Yeah, you're good. Let me just say one last thing. No, I won't say one last thing because it's 10:45. Okay, this is a good place to end. I will let you look at the notes. So look in the posted notes at the variable coefficient problem that comes at the end of the discussion we just had. Okay, looks like a good place to end. Just as a reminder, I have office hours today from 4 to 5. They'll be on this same Zoom channel. I'm going to change the office hours one of the days, Tuesday or Thursday, to Wednesday, just so we can have a different, hopefully open up some opportunities for other people to join. I couldn't do that this week because I had another meeting scheduled on Wednesday at that time. Otherwise, assignment number 2 will be posted sometime tomorrow, and assignment number 1, don't forget, that's due Tuesday. I'm going to have some instructions on how to do PDF generation with your phone, just in case you haven't done it before. I'll have that up sometime over the weekend. Okay. I will stay on, but I will stop recording.